क्या आप भी ऑप्शन ट्रेड करते हो? फिर तो आपको पता ही होगा कि
Sir, shall we start the session?
Sir, shall we start? Yes, Lokesh. We'll start. Lokesh?
Sir, shall I
Yes,
start?
sir. Shall I start, sir? Lokesh?
Yes, sir. My voice is audible to
Yes,
you.
sir. My voice is audible to you. My audio?
Yes, sir. Audible, sir. Audible, sir.
Yes, sir. Audible, sir. Yes. Thank you. Okay, sir. Hello.
Okay, sir. இந்த இது சொல்றது நார்மல் இன்ட்ரோடக்ஷன் சொல்லியிருந்தானே சார்?
இப்போ நான் சொல்லிடுறேன்.
ஓகே சார். சரிங்க சார்.
Greeting to everyone. Lokesh?
Sir, your voice is audible, sir.
Yeah, thank you.
Okay, sir.
Good evening to everyone. On behalf of Department of Civil Engineering, P.S.V. College of Engineering Technology, we extend warm welcome all of you for a 6 days online faculty development program on emerging smart technology and sustainable innovation for environmental and urban development. So we take this opportunity to thank our chairman, Dr. P.S.V. sir, P.S.V. Group of Institution, our secretary, Dr. S.V. sir, P.S.V. Group of Institution, and our esteemed principal, Dr. P. Lawrence sir, and my beloved HOD, Dr. M.P. Sanjeev Kumar sir, for encouraging conducting the 6 days online program. Also, I thank today's resource person, Dr. P. Lakshmikantan, Senior Scientist, CSAR, Bangalore. I hope this FTP, 6 days FTP, we should be informative and interactive to all the faculty members those who are joined. Now I request Dr. S. Mukesh, Assistant Professor, Department of Civil, introduce about today's chief guest. Thank you.
Thank you, sir. Good evening to everyone. It is my privilege and honor to introduce our chief guest for today's session program. Dr. P. Lakshmikandan sir. He is currently serving as a senior scientist at CSIR 4th Paradigm Institute, Bangalore, and he has illustrated careers spanning over 11 years of field of teaching and research experience, geotechnical engineering and wastewater in specialization. He has made significant contribution through advanced research in those area widely respect for his expertise. Uh, Dr. Lakshmikandan sir has successfully secured funded research funded worth of 4.15 crores from DST, CSIR, CBCB, and Regal uh, Hin- Hindalgo Industries, with several projects are going. A few several projects are completed, and few projects are currently under process. His academic research contribution, including 25 research journal reputed as Scopus SCIE publications, and 10 international conference, and 8 national conference, and 1 technical articles in the book chapter in 4 book chapter. Presently, he guiding 4
4
PhD
PhD
scholars,
scholars,
and
uh,
we
and
extremely
we extremely
to have such a distinguished personality as today grace this occasions
grace
and
these
share his
occasions
valuable
and
insights.
share his
On
valuable
behalf of
insights.
the Department
On
of
behalf
Civil
of
Engineering
the
and PhD
Department of
College of
Civil Engineering and
Engineering
PhD College of Engineering
and Technology, I
and
extend a
Technology, I
warm and
extend a warm and
respectful welcome to our
respectful
honorable
welcome
chief
to
guest,
our
Dr.
honorable
P.
chief guest,
Lakshmikandan sir.
Dr. P. Lakshmikantan sir.
May I now request him
May
to
I request
kindly
him
accept
to
our
kindly
invitation
accept
and
our invitation
enlighten
and
us with
enlighten
his
us
valuable words,
with
sir.
his valuable
Thank you,
words,
sir.
sir. Thank you, sir.
Thank you, Dr.
Thank
Lokesh.
you.
Yeah.
Thank you, Lokesh. Now the session over to Dr. Lakshmikandan sir.
First of all, thank you for inviting me as a resource person. I'll be very much happy to share my knowledge and application of whatever I have learned, especially geotechnical engineering and geoenvironmental engineering. So, go into the topic. I'll just share my slides. Uh, is it visible now?
Yes, sir, visible.
Yes, sir, visible.
Okay. So, as requested by Dr. Seduraman, we are looking at as a main branch of civil engineering, geotechnical engineering is one of the main branches. We'll try to see what is the applications, how it is useful in others, other streams, or in bringing together a lot of other issues and solving them. So why geotechnical principles are, there are a lot of you people must be knowing that there are a lot of issues which need to be addressed that are with respect to soil, that are with respect to water. When I say soil, water, or air, it's not just alone soil or water alone, it's the interaction of all the three. So it is very difficult to figure out and find a solution to those kind of things. And because of that, it is very very important to study those
Yes,
things.
sir, session was started.
And
Okay, ma'am.
how are
I
we
will send the
going to
link
do that, and why
once
GT
again.
principles come in here is
Okay.
say for example analyzing the failure of foundations, designing a safe land disposal, you know containment for wastes, maybe municipal solid waste, or hazardous waste. That has also become a very very huge problem nowadays, especially in developing countries like India. Assessing contamination and polluted sites, so it may be industry sites, or it may be other sites also, like nuclear sites, or many other things. So the principles of our geotechnical engineering or soil mechanics is used in these applications to determine the parameters, and then try to design or try to apply these things in a very very effective manner. So if you come to applications, I don't have to what to say tell you this. So if you take geotechnical engineering, it is like it's like applied into everywhere. If you start from structural, yes, it is linked to structural. It is linked to transportation. Principles are applied there. Construction, environmental engineering, earthquake, yes, hydraulic engineering like dams, groundwater drainage, marine geotech, mechanical, rock mechanics, etc. Geology, geological engineering, geomaterials, hazards, etc. So all these things come into picture, and all these things have a very close relationship to what to say geotechnical engineering. So if we take applications, let us check, or let us take the cases of what to say waste here. How the geotechnical principles are applied into waste management, or effective waste management. Now you might be wondering why it has to be waste. Um, why municipal solid waste? Because uh, some time back, like close to 5 to 10 years back, waste management was such a big issue. We didn't have any solution, and the issue was so rampant that everybody was running here and there to find a solution and how to sort it out, what to do, and all those things. So we at IISc were the first ones to study the engineering properties of municipal solid waste using the geotechnical principles, and determine all the effectively design, like a containment system based on that. Though these things were like available, or these things were being done at a very what to say normal level in the foreign countries, in India it was still to be explored. So what we did is, like we tried to use these principles to determine the properties, because as you know, municipal solid waste is a very very heterogeneous material, and it is not easy. As you know that geotechnical principles deals with mostly homogeneous material like soil, sand, etc. So we tried to do that. Now, when it comes to waste, what are the properties that we knew at the time? It's like just the basic physical properties or the composition, like what it contains. Maybe different types of waste like plastics, or some cloth like material, some inert like material, some soil like material, some organic content, etc. But then when all these things come into one or get mixed into one, it becomes a proper cocktail, which is very difficult to dispose, or which is very difficult to treat. So that is when we tried to get in geotechnical principles. So what is that further? Geotechnical principles means what tests we did, what and all experiments we performed in the field as well as in the laboratory, and what it we arrive at. I'll just take you through this journey, and also finally give you the applications using this principle, how it can be done. Like I said, let us take the classic example of waste. What you see is a landfill. Imagine the height of the landfill. This is a landfill in Delhi. It is known as Ghazipur. The height of this landfill is almost 70 to 80 meters. So you must have seen a lot of what to say issues with respect to the failure of landfills, with respect to the stability of landfills, with respect to the leachate that is coming out of the landfills, all these things. So people were clueless. So this was one such thing that had come to us, and we had taken up this as a challenge through a DST project, that we would find out a solution. So there were multiple issues. One is with respect to the stability; it used to collapse. Then there were, like issues of fire. It's like rampant fire. It's like not anyone deliberately putting fire, but then it is kind of fire on its own. So along with that, seepage, leachate during the rainy season. So if you see all these things, some way or the other, connected to our geotechnical engineering or principles of geotechnical engineering. So that is how it was decided that we'll try to see or address how it can be done. So this is like you can see the mountain of garbage here. So like I said, all these, why I'm showing this picture from a top view is, you can see all the what to say houses here and all those things. One minor collapse, and all these people will be gone. This is like basically the areas that is surrounding the landfill. It's like a slum, and then one slip or instability issue, it will destroy all the houses, and then it will be like under the
இல்ல இல்ல
like
presentation தெரியல.
a slide. Like whenever the landslide happens, it completely engulfs
எனக்கு
everything,
lag
whatever
ஆகுது
is
ஒரு
beneath it,
நிமிஷம் இருங்க.
something like that. The waste would engulf that.
ஒரு
So
நிமிஷம்.
we had to prevent it, and then give suitable suggestions or designs to prevent that. So you can see that this is
யாரோ
on top
ஒருத்தர்
of it.
மெசேஜ்
Like I
அனுப்பிச்சாங்க
said,
உள்ள
the
இது
fire also
ரெஜிஸ்டர்
is
பண்ண
an issue. So
முடியலன்னு
it's fire means it's not complete fire. It's like smoldering like this. It will be like slowly burning, and then there'll be smoke coming out of that. You can see this. This is at the top of the landfill. Now, coming to the status of municipal solid waste landfills in India, it is good to know before we start what was the issues and how it happened or what is the thing. So, when we just analyzed these things, we came to know that around 70 to 90% of the urban solid waste is being disposed of into the landfills, and most of the landfills are not scientific or non-engineered. So, urban India generates around 65 million tons of waste, and it's predicted that by 2030 it would increase to 165 170 million tons. And out of that, 43 million tons of waste is collected annually, which out of which 31 is dumped in the landfill, and just 11.9 or 12 is treated. 12 million is treated. So you can imagine the scenario or situation or the seriousness of the situation. So coming to the other facts, landfill ranks the third major source of anthropogenic methane emission. So this methane emission is one of the major factors for this fire. Why methane is having 28 times more global warming potential than carbon dioxide? Then waste, bio-earth or waste-like material is very toxic. It's not suitable to be used as a fertilizer also, as long as or as far as you treat it properly, only then it can be used. The biomining practices are leading to toxic waste, uh, called bio-earth accumulation, which is again leading to further issues like microplastics or contamination of other sort. So urgent need of cost-effective technology to utilize this also was one of the primary objectives. So like I said, what is waste? It's a heterogeneous mixture of materials that is generated in the urban area, which does not have any further use in the society. So they all dispose it, and as you can see, it is a proper mixture of everything. It is very difficult, and as the day progresses or as the time goes on, it just degrades, and then some of it degrades, some of it degrades slowly, some of it degrades very lately, some of it doesn't degrade. So we are dealing with such kind of materials. So coming to these, tests and techniques, what we thought is since this material is getting degraded, as a time progresses, after a couple of days when it is dumped in the landfill, the, properties or the size of that gets reduced. I'll tell you what happens in the process is once you dump it there, the larger particles or the particles that are greater than 100 centimeters or 100 that is 10 centimeter are being picked up by the rack pickers. Whatever is left out is less than 10 centimeters or even further below that. So if we study the properties of those materials, I think we would be able to come out with a solution properly, because that is the one that they cannot take, and then that is not recyclable and all those things. By the way, this retail industry of rack picking industry or rack picking is a huge industry. It's worth millions and more than that. So what basic parameters we started is that particle size distribution. So again, we use the sieve analysis there. Density, we use the density method, picnometer method. Shear strength, both direct shear and track shear tests. Compressibility, so you have your odometer test. So along with that, we also try to do some permeability test. We also try to do some stability analysis, slope stability analysis using dynamic properties. Again, for determining dynamic properties, cyclic traction tests were used in the laboratory. Even field tests were used. Field tests were used for determining the shear wave velocity in the field using a MASW multiscale, spectrometer, spectral wave analysis. So I'll explain you that and what it is and how it is being used. And of course, in the laboratory, we do this hydraulic conductivity or permeability, this things that tests to determine the hydraulic conductivity of waste and the soil. And then settlement through compressibility test, slope stability. So if you see overall, unless and until we determine these things, we won't be able to effectively design a proper containment system for this waste. So to start with introduction, I think I've said most of the things. So it contains materials like papers, plastics, glass, metals, fine, earth particles, etc. It's a proper mix of everything. So we started with the basic index engineering properties of MSW, like we do in the geotechnical engineering or soil, mechanics, and then detailed study the compressibility of the waste. So we started with the physical composition. We started to analyze what is the physical position. We collected some samples, like, quantity of waste was like close to 100 kgs, and the age of waste was around 4 to 5 weeks. By the time it was kind of partially degraded, and then that was used. And whatever waste we brought was passing through a 100 trauma, nothing but a sieve with 100 pore size. So we started with that size, and then we partially came down to less than 20 size, using different sieves, like 100 sieve was used or trommel was used, then consequently 75 then 35 then 16 or 20 likewise. So what the analysis is that, whatever we got is more was below 20 size. So further, again, for the further 20 passing materials, we, that is waste, we conducted all the experiments. So if you see here, you can see, plastic, clothes, 55% is like, earth like material or your organic content. Then other components are also there. So this, we performed it at the site, and as well as we brought it into the laboratory. I'll further show you what is the particle size distribution in the next slide. So next is total volatile solids. It is nothing but the organic content of a material. So this comes in handy. These principles comes in handy where when we are dealing with organic soils like peat and all those things. So these kind of tests are very, very. So again, the same thing was what to say, adopted here from there, trying to see how much of organic content is being present in the waste. So the standard thing is like you heat the sample in the oven, or you keep the sample and raise the temperature to 105 degrees, and whatever is left out after 24 hours is like, the moisture content. So in this case it was around 44%. Then if you have to find out the organic content from 105 degrees to raise the temperature from 105 degrees to 550 degrees in the muffle furnace, and whatever is left out is the what to say, your whatever goes off is the organic content, something like that. So the weight loss, or the the material that is gone. So you weigh the sample, the weight of the sample before and after the test, and finally you say that, this is the what to say, percentage. So in this case, the organic content was around what to say, 46%, and the rest was around 54%. That is inert. So if you can see that, it's a proper mixture of almost 50-50 kind of thing of organic content and the inert material. Now the problem here with us was, if you take this 50% of organic content, sometime or the other at a later point, it is going to degrade, or it is going to reduce in volume. It is not going to be stable. The 54% or the 50% of the inert is going to only stay there. So accordingly, we have to study or work out, because this thing was very important. The same thing happens when you deal with organic soils. So now coming to particle distribution, all these things were tests were performed as per the ASTM standards. So 60-minute sieve analysis was performed. Again, the standard sample size was 100 grams, and then the CCCU values, that is coefficient of, say, the CCCU values were calculated, and it was like 15 and 1. It was like, understood that it is well graded and absence of any coarse material in that. So this is a sample, I mean, like test. You can see that, most of the things were passing through the 10 sieve, and after that further, this is the distribution how it was. So you cannot imagine that, as the waste degrades, the size of the waste particles reduces. That's why, we took it from 20 and then further below 10 sieve. Now coming to specific gravity, why this thing is important? Because in organic soils, it's very difficult to find out what to say, what is the organic content. So sometimes, if there is no provision of determining the organic content, you can just measure the specific gravity and determine the organic content. That is, in this case, it was like around 1.33. If the first specific gravity is more than 2 or 2.5, then you can say that, it is not having that much of organic content. But if it is less than that, then obviously there is some amount of what to say, organic content in that, which needs to be dealt with properly. So here the pygnometer and the density bottle methods were used, And then it was like, as per the ASTM standards, and what we got is almost the average is this. So you can see the the waste. So this is the waste particles that was brought from the field, and then it was put into the bottles. Now coming to this biomethane potential test, why this test is being done is like, here a little bit of knowledge of the environmental field is also required, because the organic content, as it degrades, it there are two ways of degradation. One is, it degrades aerobically, and then the other thing is it degrades anaerobically. Now, when it degrades anaerobically, methane is produced. Now, why we are doing this test is like, waste. What happens in the field is like, you keep on dumping waste, layer over layer, layer over layer. And during the process, what happens is that, once you dump one layer and then 10 layers above that, the bottommost layer, there is no oxygen for that. And then anaerobic conditions prevail there. And once anaerobic conditions, or there is no oxygen there, to be very frank, and then when there is no oxygen, then your anaerobic degradation starts. It's a very congenial condition for anaerobic degradation, and then your methane starts producing. And that is how your methane produces, and then it seeps out of the landfill, creating smoke or fire, and all this problems. So we try to find out what is the potential of the waste to produce methane. That is called biomethane potential experiment. Now here again, there is no standard protocol for conducting the BMP test. So I'll just explain you the this thing setup, how it's done. Since we knew the volatile solids already that is there, and what to say, uh, now what we have to give there is, that would be the food. The organic content would be the food. But then, for the food to be decayed or eaten by some bacteria or something, we should give them the bacteria also. That is called the inoculum here. So the substrate is nothing but the food, and the inoculum is the bacteria. So here the ratio was, what to say, 1:1. Means that if you have 1 gram of what to say, food or substrate or waste, then you give 1 gram of the bacteria or inoculum, just to see how much of you know um, waste or food it can consume. So this is that experiment that we designed. You can see that, this is the, what to say, bench bottle. This is like, capillary tube that is coming from here, and coming into this bottle. So here what we have is the substrate plus inoculum. So we have waste and plus the bacteria. So simple. For that bacteria, we didn't use any hi-fi techniques. We just used cow dung water, because cow dung water has a lot of bacteria. And once the gas starts producing, it will enter through this pipe, and then it will go here, and you can see the gas that is being collected here. And because of that, the water will get displaced into the cylinder, graduated cylinder. So you can measure the gas by this, whatever it is, whatever is displaced or water is collected into the cylinder. So this is how we tried to find out, like, if we take, say for example, 100 grams of waste, how much of gas it can produce, or methane it can produce, because it is very important to say or determine how much of gas it will be produced, and how it is going to escape from the waste layer. So all those our issues of pore pressure, all those things will come into the picture there. So the simple equation that is called the Compet's equation, that is used to model the rate of degradation. So this is how it is. You can see that initial phase is a what to say, settling phase, or the lag phase. Means that initially there is no production, because bacteria needs some time to mature. And once it starts matured, like starts producing gas, that is the time when your methane starts generating. So initial 15 days or 16 days is the lag phase, and after that the methane starts producing. So you can see that 1 2 3, almost, what to say, 15 ml. So this experiment was carried out for more than 80 days, and after that, I think there is no what to say, increase in what to say, waste, sorry, the gas generation. And then because of that, it was like, we thought we'll stop it. So you can see here, this range of 14 to 16 liters per kg of dry waste. The quantity of methane varied between 29 to 42 percentage. So once we get this, then we know that some gas is being produced, and accordingly, either we have a Either we have a gas venting system or gas removal system, because it doesn't destabilize or disturb the what to say waste layer when we compact it, and also doesn't failure. It doesn't lead to any failure. It's the same thing. Now, coming to the engineering properties of waste, why this is important is like, when we are designing a containment system or a, what to say, a proper engineered landfill, the behavior of the waste body or the waste controls many aspects of the landfills, like, the lining system, the performance, including the stability issues, the integrity of the geosynthetic material, because as per the rules, a lot of geosynthetic and lining materials should be used. Coming to the knowledge of waste engineering properties is required to assess the potential modes of failure. That is the most important thing. So, as per this thing, we'll be able to summarize the measurement and interpretation of the parameters like compressibility, shear strength, or stiffness, hydraulic conductivity, and then apply it to effect